As I mentioned in the previous lesson, there's a relationship between sine and cosine, and we'll explore that today. And the special relationship is because of the complementary angles. Before we get too far, your friend SOHCAHTOA is our helpful reminder. So if we focus on sine and cosine today, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. And then when you get to IXL, you'll also be using tangent, which is opposite over adjacent. So on the previous lesson, we saw this slide and we noticed that, hey, sine of S and cosine of R have the same value. Cosine of S and sine of R have the same value. And I said we'd get back to that. Now, of course, for any triangle, we know the three angles have to add up to 180 degrees. We also know that angle T is a right angle, so it has to measure 90 degrees. Of course, if I subtract 90 degrees from each side of that equation, I can figure out that angle R and angle S have to have measurements that add up to 90 degrees, which means that angle R and angle S are complementary angles because their sum is 90 degrees. And so that creates this special relationship between sine and cosine when we're looking at complementary angles. So that's what we noticed yesterday. The functions are equal to each other when they're looking at the complements. Of course, that subtraction is just how we quickly find the complement. If we know one of the angles, we just subtract it from 90 degrees to find the complement. Now again, this only works if A and B are complementary angles, right? A and B, when we add their measurements together, has to add up to 90. So let's see, does sine of 30 degrees really equal cosine of 60 degrees? Right, 30 plus 60 adds up to 90, so those are complements. Let's see if we can find the exact value of sine of 30 degrees and the exact value of cosine of 60 degrees. No, we're not going to grab a calculator. Don't get silly. That picture won't help. Let's draw a triangle. So I need a triangle. Oh my goodness. We know this one. It's the 30, 60, 90 triangle. The hypotenuse is 2. The short leg is 1. The long leg is root 3. Of course, the short leg of 1 has to be across from the smallest angle, which is 30 degrees. And then the longer leg, root 3, has to be across from the larger acute angle, which is 60 degrees. Of course, the largest side, the hypotenuse, always has to be across from the right angle. Well, sine is opposite over adjacent. Over hypotenuse. Woo! Right? Sine is opposite over hypotenuse. Opposite of 30 degrees is 1. The hypotenuse is 2. There's the exact value for sine of 30 degrees. Cosine is 60 degrees. Well, adjacent leg would be 1. The hypotenuse would be 2. Sure enough, they have the exact same value. Sine of 30 degrees really does equal cosine of 60 degrees. Okay, if I give you sine of 40 degrees, what would that be equal to if I wanted to use cosine? Well, sine of 50 degrees? I'm sorry, tongue-tied here. Sine of 40 degrees would have to equal cosine of 50 degrees. How do I know that? Well, 90 subtract 40 is 50. Right? Those are complementary angles. What if instead I start with the sine of 73 degrees? Well, that would have to be equal to the cosine of 17. Again, why is that the case? 90 subtract 73 is 17. What if instead I start with an expression in terms of cosine, but I'd really rather work with sine? If I was given a cosine of 27 degrees, what would that be in terms of sine? Well, it'd be the sine of 63 degrees. That's because 27 and 63 are complements. What if I start with the cosine of 48 degrees? Better grab your Hitchhiker's Guide to the Galaxy, because here comes 42. Right? 48 and 42 are complements. So the cosine of 48 degrees has to equal the sine of 42 degrees. Now, we've been down this road before. We've already talked about our special right triangles. We've already talked about not leaving radical denominators. So when you get to IXL today, this is one of the things I got to talk about. For example, if I wanted tangent of 30 degrees, using SOHCAHTOA, I can remember that tangent is opposite over adjacent. If I'm at 30 degree angle, the opposite side is 1. The adjacent leg would be root 3. I cannot leave a radical denominator. If you try to type that into IXL, you will get it wrong. Instead, I'm going to multiply by the number 1, but I'll disguise the number 1 as root 3 over root 3. On top, in my numerator, 1 times root 3 is root 3. On the bottom, in the denominator, root 3 times root 3 is root 9. Of course, the square root of 9 is plain old 3. I now have an exact value for tangent of 30 degrees with a So that's one of the things going on with IXL today, is that you're going to want to use your friends, those special right triangles. You want to make sure that you can manipulate any fraction so you do not have a radical denominator. But here comes the really weird twist that's going to show up here. We're just going to study sine, cosine, tangent. That's what we do in geometry. IXL must think we're like superstars. So I want you to work with sine, cosine, and tangent. That's what the SOHCAHTOA reminds us to do. That's what we can do with our special right triangles. For some reason, IXL seems to think that we should be working with all 6 trigonometric functions. We'll probably introduce cosecant, secant, and cotangent in Algebra 2. You will definitely use all of them in pre-calculus and calculus. But for the purpose of geometry, sine, cosine, and tangent is all we need. So I worked on this and I got to a score, I think I got around 72 or so when it started asking about cosecant, secant, and cotangent. So I want you to keep working as long as they ask you about sine, cosine, and tangent. You should do fine with those. But before you hit a score of 80, they start throwing in the other functions, and we've not looked at them, and we're not going to look at them this year. So when you start seeing something like the CSC, that's cosecant, or if you ask to find a SEC, that's secant, or you see that COT, cotangent, go ahead and stop working. Right, so your score will be somewhere around 70, maybe slightly above 70 before you say, whoa, this is something we've not covered. So we want to look at R5. You'll be finding the trigonometric ratios for our special angles, which means you'll be looking at that 45, 45, 90 triangle, and you'll be working with that 30, 60, 90 triangle. How they get the cow to pause that long for that sketch is beyond me. Nice bandana though.